Alright, so here's the last video for Unit 6, talking about Bernoulli's equation. And so again, we're going to keep talking about fluid dynamics, so what happens when a fluid flows. So when a fluid flows into a narrow channel, its speed increases, which means its kinetic energy will also increase. So Bernoulli's equation, we'll talk about here in a second, is just really looking at conservation of energy of fluids, right? And so this concept comes from the continuity equation, right? A1 V1 equals A2 V2. So once I start constricting the area in which the fluid can move, that means I'm going to increase the speed, right? So remember, area and velocity have an inverse relationship. So the smaller the area, the larger the velocity, right? And so if we do our relationship, big area times little velocity equals little area times big velocity, right? So therefore, there is a pressure difference when the channel narrows. So the pressure will drop in a rapidly moving fluid, whether or not the fluid is confined to a tube. So here's what I want you to think about. This is the reason why airplanes lift off, okay? And so here's my airplane wing, right? Something you notice that they're bigger on top, they're more curved on top than they're on the bottom, because if I have air flowing and hitting the front of the wing, what happens is the air will split. Some of it will go over the top, right? And some of it will go under the bottom. But they have to meet up together here in the end, right? We'll make it 4, right? So what does that mean? Again, here's my wing, right? Color my wing in here purple. So this is my wing, right? So what happens is the air on top moves faster, because again, it has to move, it has to meet up with the air on the bottom at the end. It has more to travel, and for that to happen, the air on top has to move faster where the air on the bottom moves slower, right? So what does that mean? There's low pressure up top and high pressure on the bottom. And what happens is, because of that difference in pressure, so we can find a color that would suffice, right? There is an upward force, right, that we call lift, right? And that's why airplanes are able to lift off, right? Spoilers on cars are the opposite of this, right? So imagine taking this diagram I just drew and flipping it over, right? Which it creates a down force. And so that is the idea, right, that we're talking about here. So the relationship between pressure and velocity in fluids, as described quantitatively, right, or is described, it should be is, not as, quantitatively by Bernoulli's equation. And this is one of the reasons why fluids and states of matter I really wish was taught more, right? Because this is a very practical way to think about this, right? And so basically you've got 3 components. You've got P, you have rho GH, and you have 1/2 rho V squared, and that's equal to a constant, okay, where P is the absolute pressure, which it may be atmospheric pressure, it may be given to you, okay. Rho is the density of the fluid, V is the speed of the fluid, H is the height above some reference point, and G is the acceleration due to gravity, or 9.81. Now, another way to write the equation, and the more practical way to write it, is to set it equal to, or it's kind of like conservation energy, where we set the total energies equal to each other. It's kind of like we're doing the same thing, but we're setting the total pressures equal to each other. Okay, and so that would be like if I had something like this, right? And if this is my H equals 0, it's flowing here has a V2, a V1, right? This is H2 or H1. This is H2 equals 0. So again, just like what we did with conservation energy, we write it all out, cancel things out where we need to. Right here we'd have a pressure here, we'd have a pressure here, and so we're able to find different things. We can find the speed, we can find the height, we can find the density, we can find all this fun stuff. Okay. Now, if the fluid is static, notice what happens. Right, your your V is 0. Well, that equation should look very familiar, because that is the absolute pressure equation that we talked about a couple videos ago. Okay, now if the fluid is flowing at a constant depth, right, you can get rid of the H's, and so it just reduces down to be, right, P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Okay. Alright, so the example in a water hose, or if we go back and revisit the water hose example, it says the water in a hose increases from 1.96 meters per second to 25.5 meters per second when going through a hose to a nozzle. Calculate the pressure in the hose, given that the absolute pressure in the nozzle is atmospheric pressure, as it must be. So here's the thing. If it's open to the environment, your pressure is atmospheric pressure. Right? If it's closed, it's got to be given to you. And so what's happening here is, in the nozzle, because the nozzle is open to the environment, it experiences atmospheric pressure. But in the hose, because it's closed off from the environment, we're finding that pressure. So we're finding that absolute pressure. So we're going to use the second equation that we wrote up there, so that you kind of see at the top. So P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. And let's just say, for giggles, we're going to solve for P1. So what we're going to do is we're just going to solve this for P1. So P1 equals P2 plus 1/2 rho. And I'm going to do a little bit of algebra in one step. So basically what I'm doing is I'm subtracting this over. But because the density is the same, I'm just going to pull that out. Right, and 1/2 is the same. I'm just going to clean up my algebra a little bit, make it easy to plug into my calculator, or write it. So I know once it comes out, it has a pressure of atmospheric pressure. So 1/2 times 1,000 times 25.5 squared minus 1.96 squared, and that will give me the pressure in the hose. Now, before we actually do the calculation, because it's slower, it should have a higher pressure. If it was moving faster, it would have a lower pressure. And you can see that because, look here, this will be positive, which means this stays true to be a positive sign. If they were flip-flopped, right, I would have a negative inside here, which actually then turns out to a minus sign. And so now when I plug it into the calculator, I get 4.24 times 10 to the 5th pascals, right? So basically, remember, slower speed equals greater pressure. Okay. Now, we talked about the two examples. So, two common examples, right? Wings on airplanes. If you go back to the beginning of this video, we talked about that, and then spoilers on cars. Right, and so a spoiler is basically the reverse of a wing. So if I have 4 air units coming in here, right, 2 are going to go over the top, 2 are going to go underneath, but again they're going to meet up at the same time to become those 4 air units again, which means that this is now going to be slower and this will be faster, which means slower speeds, greater pressure, right, or high P. This will be low P, which means now my force will be a downward force that we call downforce, right? And so this will keep the tires on the ground, right? If you think about NASCAR, Formula One, IndyCar, right? They have spoilers on the cars. NASCAR has the added safety feature of roof flaps, which create this this kind of situation, which keeps the cars on the ground. And that was out of necessity because there were some major accidents where cars went flying, hurt fans, hurt the drivers, so they had to figure out a way to keep the cars on the ground. They put their heads together in research and development and came up with these roof flaps. Okay. Now here's a question that may show up on the test or something similar to it. It says, suppose that a huge tank 50 meters high is filled with water. Water is open to the atmosphere and is hit with a bullet that pierces the side of the tank, allowing water to flow out. The hole is 2 meters above the ground. If the hole is very small in comparison with the size of the tank, how quickly will the water flow out of the tank? So basically here's what we have, right? We have a tank full of water open to the environment, which tells me that my pressure at the top is going to be atmospheric pressure, so 1.01 times 10 to the 5th pascals. A bullet comes through, pierces it, right? And it's going to kind of come down and hit. And we're trying to find what is the speed as it comes out. Well, again, you have to remember, this is going to now be open to the environment, so it's going to have an absolute pressure of 1.01 times 10 to the 5th pascals. We know when measured from the ground, this is 2 meters, and then the total would be, or the tank is 50 meters. Okay? And so you could do a couple things here. You can subtract out this height and say, okay, this is just going to be 48 meters, which basically puts my h equals 0 at the hole, which is something you can do, which is fine. And so if we go and do our Pascal's principle, so P1 plus 1/2 rho V1 squared plus rho G H1 equals P2 plus 1/2 rho V2 squared plus rho GH2. Okay, and so if I move everything up like we did with energy and roller coasters, right, I'm essentially making one of those two 0, so I'm going to make this 0. Now at the top it's considered to be a static fluid, right, so it doesn't matter, right, it's not moving. The pressures, the absolute pressures, are equal because they're both open to the environment, so it's just atmospheric pressure, which then just tells me it's rho GH1 equals 1/2 rho V2 squared. And the way you think about it is this is all pushing down, right, causing the water to come spewing out of here. Okay, so densities are equal because it's all the same liquid, it's all the same water. You could say, in fact, it does say water, right? And sometimes it may just say it's filled with a fluid, so it doesn't matter what it is. And so all I'm going to do is solve this for V2. So V2 squared, or V2 equals the square root of 2GH. Oh, H1, sorry, not H2. Right? The equation looks very familiar because conservation of energy. Right, so 2 times 9.81 times 48 will tell me how fast that water is coming out at the bottom. So V2 equals 30.7 meters per second. Now, what they like to do with these questions, and you may see this on the homework, in fact, I've looked at the homework, it is on the homework, they may do something with like how far out does it land, so it brings in projectile motion. Okay, they may do something crazy where they cap it and tell you the pressure on the inside, and then then they shoot the bullet at it. So there's just different things they can do. The only for that question, if they cap this, is these two do not cancel out now. Okay, so that ends Unit 6 with solids and fluids. Again, this is a very fun unit. I just wish that was taught more in physics. Because I think there's a lot of cool things, and a lot of people want to become doctors. A lot of people want to join the Navy, want to join the Air Force, want to become pilots. This is more conducive to students, to you guys who want to do stuff like that. Okay, so we now have only 2 more units to go. We have Unit 7, which is going to be sound, and then we have Unit 8, which is going to be heat and heat transfer.